Thank you to everyone for joining me this morning. As I was going through the examiner's report for question 14 in the 2016 B paper, which is describe the principles of how a computer-controlled infusion device targets and maintains a constant effect site concentration of propofol. One of the key statements that was made by the examiner was that the central role of KEO in the pharmacokinetic relationship between the central compartment and the effect site should be emphasized. And this got me thinking that we really needed to have a session on KEO because KEO is such an interesting pharmacokinetic concept, but an extremely difficult one to understand, which is probably why it is not taught well at all. But I hope to change that today. It is grounded in some core pharmacokinetic concepts such as clearance, volume of distribution, elimination rate constant, and half-life. And knowing these concepts will help you in your understanding of how KEO works and allow you to answer the following question, which is, why does a larger elimination rate constant, in other words, proportionately more drug is being removed per unit time, lead to a faster time to peak effect? The literature review that I've done, or the resources that I've used, are Pharmacokinetics Made Easy by Donald J. Burkett, chapter 18 and 26 in Miller's Anesthesia, and lots of journal articles. Too much to list on the slide, but the authors are all the core authors of pharmacokinetics. So there's Struess, Schaefer, Schneider, Marsh, and a lot of others as well. Now, the definitions that we need to have clear in our head. So first one is clearance. Clearance is the volume of plasma cleared of a drug per unit time. And the key words are volume of plasma. Whereas when you compare that to elimination rate is the amount of drug in plasma removed per unit time. And so the question that I often get asked is, why plasma and not blood? The reason for this is because when we take a drug sample, or when we want to measure the concentration of a drug, we often measure it in plasma. So quite often when you want to take blood, what they'll ask you to do is take it into one of these yellow tubes where it has a gel at the bottom. And after you get this down to pathology, it gets centrifuged and it gets split. So it gets split into plasma. It's got that gel here is a separator. So you got the gel. And then after that, you've got your red blood cells. And what the pathology does is that it measures the concentration of the drug in plasma, okay? Which is why these definitions exist for plasma. And if we look at this diagram here, when we talk about clearance is the volume. So it's this amount here. It's the volume of plasma cleared of a drug per unit time. So it's the volume of this compartment here. Whereas when we talk about elimination, it is the amount of drug. So it's what's inside the volume. And you can see that relationship already. So that when we talk about elimination rate, which is the amount of drug cleared per unit time, it equals to clearance times the concentration. So if I was to explain it in terms of words, it's the amount of plasma that's cleared per unit time multiplied by the current concentration of the drug within that volume. And it is important to note that even though we use plasma, the organs that eliminate drug are perfused with blood. not plasma. However, the ratio of drug concentration in plasma and red blood cells is approximately 1 for most drugs, which is why it's okay to use plasma for these definitions. However, if you do hear someone using blood, it is completely acceptable. Or if you want to use blood, again, it is completely acceptable because the ratios of the drug concentrations between plasma and red blood cells, okay, for most drugs is approximately 1. Now, the only caveat are drugs which are highly concentrated in red blood cells. And the example that's often given is cyclosporin. At steady state, the maintenance rate equals the elimination rate. And that should make sense. In other words, what we're doing is we are replacing the drug that is being removed so that you maintain a constant or steady state plasma concentration. We know from the previous slide that the elimination rate equals clearance times concentration. And if you you substitute elimination rate with maintenance rate, we get maintenance rate equals clearance times concentration. What we're going to do is we're going to define clearance in terms of maintenance rate. And what we have is that you move concentration over to here so that clearance equals the maintenance rate divided by the concentration at steady state. And this is important to know because pharmacokinetically, when they do the mathematical derivations of what the clearance is for a drug, this is how they find it out. They find out what the steady state concentration is, and then they find out what the current maintenance rate is. And by doing that and using this formula here, they're able to calculate what the clearance is. Now, the other way to calculate clearance is with this formula. So it's dose divided by the area under the curve, okay? And the area under the curve has units of mass time divided by volume. This curve is actually a little bit confusing. And the thought is that the reason why it's confusing is that when you integrate concentration versus time, don't you get dose? And the example that's always brought up is it's very similar to integrating flow versus time to calculate tidal volume in a ventilator. And obviously the answer is going to be no from that previous example before. And the reason for that is that concentration is not defined by time like flow. So flow has units of volume over time, whereas concentration has mass over volume. And if you actually want to calculate the dose, the one you have to integrate is maintenance rate versus time. So maintenance rate has units of mass over time. So the question now is, what does the area under the curve represent? And it represents the total drug exposure across time, where its units are mass time divided by volume. So that's an important thing to note, is that when you are looking at the area under the curve for a concentration versus time graph, you're looking at the total drug exposure across time. And theoretically, that can actually be more than the actual drug that's given. So what I mean by that is that if you look at the graph below, normally for a bolus dose or for a drug that you give as a bolus, it should look something like this, where it'll come down. But if the clearance approaches 0, this curve will just continue on as time reaches infinity, and the area under the curve will reach infinity. And if you look at the calculation below, as the area under the curve approaches infinity, clearance will start approaching 0. okay? And that should make sense to you in terms of if you give a bolus drug and it's not being cleared in the body, that drug is going to persist for an infinite amount of time. And this is just a theoretical example. There would be no drugs that would have this, but it just shows you the power of this formula here. Now, the next concept that we need to talk about is volume of distribution. So volume of distribution is the theoretical volume that contains the total drug at the same plasma concentration. So what do I mean by that? So let's say you have an unknown volume here, okay, and you have given a drug. So you have a total drug here, which is represented by X. And you calculate or you draw a sample out of this unknown volume with a known concentration. So after you take the sample out, you measure it, and now you've got a known concentration from here. And by knowing what the concentration is from this little sample, you can calculate what this volume of distribution should be so that the concentration here with the total drug equals the concentration here. So the formula that they use is dose divided by concentration. Now, this is important because depending on when you sample the concentration, you can have different types of volumes of distribution. And that's why with the different texts that you'll see different ones being quoted, and you might see different numbers as well. And the reason for that is because that there are multiple volumes of distributions that you can use. So VD1 is called the volume of distribution of the central compartment, which is measured at peak plasma concentration. The volume of distribution of peak effect is called VDPE. And then after that, you also get the volume of distribution at steady state. And there are multiple others that you might see as well. So you might see the volume of distribution 2, or you can also see the volume distribution of the initial distribution, and also the volume distribution of compartment 3. So there are various different types of volume distributions that you can see. Okay. Now I'm just going to illustrate it in the next example. So this is a propofol versus time graph, and the units that we're going to have is often mics per mil, or we can often change it to milligrams per liter. And hypothetically, let's say we give a dose of 100 milligrams of propofol. So we've got 3 things here that we need to calculate. So we want to calculate the volume distribution of the central compartment. So that's about 20 milligrams per liter. And we know that the formula equals dose divided by your concentration. So the dose here is 100 milligrams divided by the concentration, which is 20. And so VD1 equals 5 liters. Now, the blue line here represents the effect site. And at the peak effect, you have a plasma concentration of 10 milligrams per liter. And so 100 divided by 10 means that the volume of distribution at peak effect equals 10 liters. And finally, you've got the volume of distribution at steady state. So here, and that's about 5 milligrams per liter. So 100 divided by 5 equals 20 liters. And that equals the volume of distribution at steady state. Why is this important? It is important because it allows you to calculate a dose to reach a target concentration. So in other words, that if you have a known volume of distribution, what we're going to do is we're going to reverse the formula behind, to reverse the formula back, so that we can actually calculate what the dose should be to reach a specific target concentration. So what do I mean by that? We're going to use fentanyl as an example, okay? And we know that the formula is VD equals dose over concentration. But what we're going to do now is that we want to calculate what the dose should be. So we're going to define dose equals volume of distribution divided by concentration. So to calculate the loading, we're going to calculate now the loading dose of fentanyl to attenuate the hemodynamic response to intubation. And the reason why I've chosen this example is that this is something we do every day. And the fentanyl's C50 for hemodynamic response to intubation is 3 nanograms per mil or 3 micrograms per liter. And the C50 is the concentration associated with 50% response of the effect. And just as a reminder, the C50 can also be known as EC50 in a graded response curve. So that's the same thing. So the C50 or EC50 are the same concepts, okay? So now we're going to calculate what dose we should give. And you can see in this example here that we've got known volumes of distribution for the different types. So VD1 is 13 liters, the volume distribution at peak effect is 75 liters, and the volume of distribution at steady state is 360 liters. And using the formula, dose equals volume of distribution times concentration, we get a dose of 39 mics, so 39 micrograms, 225 mics, or 1,080 mics. And immediately that you can see that depending on which volume of distribution you use, it changes what dose you have. And clinically, the ones that we will use for this is the volume of distribution at peak effect of fentanyl, which occurs at 3 to 5 minutes. And that is why this is the type of doses that you will see being given to attenuate the hemodynamic response to intubation. So 200 to 300 mics in the average 70 to 80 kilogram person, okay? The next concept that we're going to talk about is half-life. And I'm going to start talking about half-life in zero-order kinetics. So when we are talking about the elimination of a drug, half-life is the time taken for the plasma concentration of a drug to fall by half. But for zero-order elimination, half-life decreases as concentration decreases. What do I mean by that? So as your concentration decreases by half, so let's say we go from 10 to 5, you can see that the half-life here is 5 hours, okay? Now, in the next segment where it goes from 5 to 2.5, so as concentration goes from 5 to 2.5, you can see that the half-life here decreases from 5 to 2.5, okay? And then as you go from 2.5, so as it halves again, you can see that the half-life again shortens to 1.25. And the reason for that is that the elimination rate is fixed, is a fixed amount. So it's not dependent on the concentration. It is a fixed amount per unit time in a given volume of distribution, which is why that as your concentration decreases, your half-life decreases. Now, I'm going to explain this mathematically. So in zero-order kinetics, the rate of change equals K, where K is defined as the zero-order rate constant. And its units are mass divided by volume time. So in zero-order elimination, plasma drug concentration after a single dose is described as a linear decay function. So in the previous slide, we drew a straight line. There was a straight line. that represented a linear decay function. And the formula for a linear decay function is that concentration with respect to time equals negative K with respect to time plus the initial concentration of the drug. And to differentiate that function, or to find the rate of change, the answer that you'll get is minus K. So this tells you that the rate of change is a fixed amount per volume time. It is independent of the current plasma concentration, and the elimination rate is constant in a given volume of distribution. Now, let's go back to the previous slide again and look at this. So for zero order elimination, and let's assume that this has a volume of distribution here of 1 liter to make the maths nice and easy. When we look at the first 4 hours, so the first 4 hours here, you've got a drop of concentration from 10 to 6. And therefore, the rate of change is 1 milligrams per liter hour. And if you have a volume distribution of 1 liter, it means that your elimination rate is 1 milligram per hour. Now, if you look at the next 4 to 8 hours, so the next 4 hour period, again, you've got a drop from 6 to 2. Okay. And again, the rate of change is 1 milligram per liter hour. And the elimination rate for that given volume of distribution is fixed. It continues to be 1 milligram per hour. So it doesn't matter what the concentration of the drug is, 1 milligram per hour is always being removed. And this is for a drug with zero order kinetics. And because the elimination rate is constant, you will see that half-life decreases. This is the one that we talk about for almost all our drugs that we use in anesthesia. This is the half-life in first order kinetics. So half-life, again, is defined as the time taken for plasma concentration of a drug to fall by half. And for first order elimination, half-life is constant, where the elimination rate will decrease as concentration decreases. So remember that in zero order kinetics, half-life decreases as concentration decreases, and your elimination rate is fixed. Whereas now we're saying the opposite with first order kinetics. Half-life is constant, but the elimination rate decreases as concentration decreases. So just to sort of show you again, as your concentration drops by half from 10 to 5, your half-life here is 4 hours. And when it drops from 5 to 2.5, your half-life here is 4 hours. And when it drops from 2.5 to 1.25, your half-life here is constant. It is 4 hours. Now, let me explain this mathematically. So in first order kinetics, the rate of change is defined by the formula K multiplied by C, where K is the first order rate constant and its units are per time. Now, K can also be described as the elimination rate constant. So that's where that terminology comes in. And C is the concentration. So in first order elimination, the plasma drug concentration after a single dose is described as an exponential decay function. When we look at an exponential decay function, and we're looking at differentiating to find the rate of change, the way that it's done, so the rate of change of concentration with respect to time for an exponential function is the exponential function. So you just type in so you're just writing the exponential function itself, multiplied by the differentiation of the exponent. And the exponent is minus k multiplied by time. And so that is multiplied by negative k. In other words, the rate of change is minus k times the initial formula. But you can simply write it as minus k multiplied by the current plasma concentration of the drug. And you can see from this formula here, okay, that the rate of change is a fraction or percentage of the current concentration of the drug. And this is important. So in first order kinetics, the rate of change is dependent on the plasma concentration of the drug. And the elimination rate at a specific time is proportional to the plasma concentration. Now, very important here, there are two concepts that are easily confused. So one is the elimination rate constant, and two is what's called the elimination rate. The elimination rate constant does not change. It's a constant. And it determines what the elimination rate is. So again, the elimination rate constant does not change, but it determines what the elimination rate is. And that can change. And the reason why the elimination rate can change is because of this formula here. Is because that it's dependent on the current plasma concentration, and the plasma concentration with respect to time changes. And so the elimination rate at a specific time is always proportional to that plasma concentration. Now, let's go back to that slide again and review this. So looking at this slide here, when we look at the first 4 hours here, where the concentration of a drug goes from 10 to 5. And so, again, we're saying that the volume distribution here is 1 liter, just to make the maths easy. So the rate of change, the average rate of change in the first 4 hours is 5 divided by 4. So that's 1.25 milligrams per liter hour. And if you look at that for a volume distribution of 1, that's an elimination rate of 1.25 milligrams per hour. Now, for the second 4-hour period, where you've got the drug going from 5 to 2.5, so that's a change of 2.5 divided by 4. And so the average rate of change is 0.625 milligrams per liter hour, where the elimination rate is also 0.625 milligrams per hour. And as you can see, that as the concentration decreases, your elimination rate also decreases as well. But your half-life remains constant. So this is the opposite of zero-order kinetics. Zero-order kinetics, you've got a half-life that decreases as concentration decreases, and the elimination rate is constant. Whereas in first-order kinetics, half-life is constant, but your elimination rate decreases as concentration decreases. And again, remember that there's a difference between the elimination rate constant and the elimination rate. So the elimination rate constant does not change, whereas the elimination rate, which the amount of drug that is removed per unit time, changes proportionately to what the current plasma concentration of the drug is. So the next concept that we need to build on is how is the elimination rate constant related to half-life? And this is for first order kinetics. So looking at the previous example, when we looked at the drug, the half-life of that drug was 4 hours. And so when you look at the formula, the concentration at the 4-hour mark equals 0.5 times the initial concentration. And the initial concentration on that previous graph was 10. And so the concentration at its half-time equals 5. Knowing that this is how the formula works, we know that the concentration at its half-time equals 0.5 times the initial concentration of the drug. And what we can do now is that we can substitute this into our exponential decay formula. So what I mean by that is 0.5 times the initial concentration of the drug equals the initial concentration of the drug multiplied by Euler's constant to the exponent of minus k, and we'll say t half at t half time. Okay, and so the initial concentrations will cancel out, and what you're left is with these two numbers here. And what we're going to do is that we are going to log both of them with respect to Euler's constant. So log e 0.5 equals log e to e minus k to t half. And the natural log of 0.5 is minus 0.693. And the natural log of Euler's constant is going to be 1. And remember that when we log this, this comes down here in front, so that becomes minus k t half. And this is the key formula to remember, okay? So the negatives will cancel out, and this is where you get all your derivations from. So 0.693 equals your elimination rate constant multiplied by your half-life. And this is where you can define it in terms of either your elimination rate constant with respect to half-life. So your elimination rate constant equals 0.693 divided by your half-life, or the natural log of 2 divided by your half-life. Or you can also describe it as your half-life equals 0.693 divided by your elimination rate constant. This is the key relationship to remember. And an easy way to remember is that the 0.693 or the natural log of 2 is always on top. It doesn't change. So what changes position is either your elimination rate constant or your half-life. And they are inversely related. So you can, so just in the top of the screen, k equals 0.693 divided by your half-life, or you can say that your half-life equals 0.693 divided by k. Now, the other way that you'll see elimination rate constant defined is that it equals your clearance divided by your volume of distribution. So here's how they've come down to this formula. So we know that the elimination rate equals the rate of change multiplied by your volume of distribution. And we also know that your elimination rate equals your clearance multiplied by concentration. And so if you have the equations 1 and 2 equal each other, you've got the rate of change multiplied by the volume of distribution equals clearance times concentration. And what we're going to do is we're going to move a volume of distribution over to here, and we're going to move concentration over to here, so that we get this formula here. We get rate of change divided by concentration equals clearance divided by volume of distribution. And with the formula on the left-hand side, you can see that the mass and volume cancels out. So mass and volume cancels out. And so now we've got K which is just respect to time, equals clearance divided by volume of distribution. And this should hopefully make sense to you. In other words, if you increase the clearance of a drug, you're increasing the fraction of the plasma concentration of the current plasma concentration of the drug that is removed per unit time. In other words, you are increasing your elimination rate constant. And when you decrease your volume of distribution, remember that drugs are only cleared from the central compartment. So if you reduce your volume of distribution and most of the drug is being held into the central compartment, it means that a lot more can get cleared, which is also why a reduction in your volume of distribution will increase your elimination rate constant. The other way that you will also see half-life being defined is through the idea of clearance and volume of distribution. And that is true from that previous formula that we have. So we know that K equals clearance divided by volume of distribution. And we also know that K, or your elimination rate constant, equals the natural log of 2, or 0.693, divided by your half-life. So if you put those two equations together, what you get is your half-life equals the natural log of 2 multiplied by your volume of distribution divided by clearance. This is the reciprocal of what I talked about with the elimination rate constant. In other words, when you increase your volume of distribution, you're going to be increasing the half-life of a drug. And if you decrease the clearance of a drug, you're going to be increasing the half-life. And hopefully that makes sense to you as well. Now, you will see different half-lives being presented. So the half-life that we've been talking about for the last previous slides has been the elimination half-life. So that is the time taken for the plasma concentration of a drug to fall by half. But half-life can also be defined as the time taken for a process to be 50% complete. And that process can be equilibration, absorption, distribution. And the process is considered to be relatively complete after 3 to 5 half-lives. And that represents 88 to 97% completion. Now let's look at KEO and its effect on the equilibration time between the central compartment and the effect site. So we're looking at how KEO affects the equilibration between the central compartment and the effect site. Now, why is it called KEO? So O represents outside. The other way that it's also being presented is KE0. And that has been presented in text as a representation that the outside compartment is also labeled as 0, because you've got V1, V2, V3, and the effect site. And so they've labeled the outside component compartment 0. So I think it's okay to use both terminologies, but the traditional way that we talk about it is called KEO. But as you can see with how it's written in a lot of text, it's written as KE0. So that's the reason why it's been presented in those two ways. So just following on with KO's terminology, the way that it's been defined as the effect site elimination rate constant, but it's also been defined as the effect site equilibration rate constant. And to explain this, KO is the effect site elimination rate constant, which determines the time to equilibration between the plasma and biophase. Question is, why? Why does the elimination rate constant determine the time to equilibration? So to understand this, we have to take a step back. And what we're going to do is we're going to take a step back and we're going to look at the equilibration between drug administration and the central compartment. So drug administration is often called KO, and K10 represents your elimination rate constant. So the question that we're going to ask and we're going to answer is that if a drug was administered at a constant dose rate, represented as KO, what determines the time taken for equilibration to occur between the infusion rate and plasma concentration? In other words, what determines the time for plasma concentration to reach steady state? The answer is a drug's elimination half-life. When we look at a drug's half-life at 3 to 5 half-lives, so at this point here, at 3 to 5 half-lives, if you maintain a constant drug infusion, you will get steady state. So at this point here, at that point. And depending on what the elimination half-life of that drug is, determines how long it takes before it reaches steady state. So if the answer is the elimination half-life, what does the elimination rate constant have to do with it? Remember the formula we talked about before, where half-life equals the natural log of 2 divided by your elimination rate constant. So this relationship here, T half equals 0.693 divided by K. In other words, that we know that the elimination half-life determines the time for plasma concentration to reach steady state. And we also know that the elimination rate constant, through its relationship with the elimination half-life, that's how it determines the time to equilibration between plasma concentration and a drug's infusion rate. Okay, so you can see that the elimination rate constant here affects what the elimination half-life is, and the elimination half-life determines the time to steady state, which is 3 to 5 half-lives. This is exactly what happens at the effect site. So the elimination rate constant, KEO, through its relationship with the elimination half-life, called T12 KO, determines the time to equilibration between the effect site and plasma. Now, I just want to show you this article here, which represents how I think about KO. So this was in Anesthesia 2014. And the way they define KO is that it's the elimination rate constant. But remember that there are many texts that will describe KO as the equilibration rate constant. Now, I've highlighted the really important bits here. So the KO is calculated based on analysis of plasma concentrations and the corresponding time profile of the measured effect. The KO can be expressed as a half-time KO. So that's the natural log of 2 divided by the elimination rate constant, or KO, will equal your T12 KO, which is directly correlated with the time of equilibration between the central compartment and the effect site. In other words, if plasma concentration is maintained stable, as in the case of plasma TCI, the time required for the effect site concentration to reach 50, 75, or 87.5% of plasma concentration can be estimated by 1, 2, or 3 multiplied by the half-life KO respectively. What we've talked about is the equilibration of the effect site and the plasma, or the plasma and the infusion at steady state. So we're talking about an infusion. When we talk about time to peak effect, we generally talk about bolus dosing. So equilibration tends to be for infusions. Time to peak effect tends to be when we talk about bolus dosing. But there are analogous in terms of the time, okay? So again, the formula here, so important. T12 KO equals the natural log of 2, or 0.693, divided by the elimination rate constant, where the elimination rate constant equals clearance divided by volume of distribution. In other words, if you increase your elimination rate constant, either through increasing clearance of a drug or decreasing the volume of distribution, you decrease your elimination half-life, or T12 KO, and that leads to a faster time to equilibration for an infusion, or time to peak effect for a bolus dose. And conversely, if you decrease or reduce the elimination rate constant of a drug, either through decreasing clearance or increasing the volume of distribution, you will increase the drug's elimination half-life, or increase the T12 KO, and that will lead to a slower time to equilibration for an infusion, or time to peak effect with bolus dosing. And with this formula, so such an important formula, we know the how. And when I talk about the how, it's how does the elimination rate constant affect time to equilibration or time to peak effect? The how is through this relationship here. But this doesn't answer up the question that we had from the start. We want to know the why. In other words, why does a larger elimination rate constant, where proportionately more drug is being removed per unit time, lead to a faster time to peak effect? So to do this, let's take a step back again and look at the pharmacokinetics of the central compartment. And you can go to this website that I have listed on the top, so www.boomer.org. And this is a really good site to play around with different pharmacokinetic variables. And this is for plasma concentration, and the components are, I have an infusion running at 10 units per unit time. And the time here is arbitrary, so it's 0 to 24, and the plasma concentration is 0 to 5. Okay. And what we see here is that as your elimination rate constant increases, so this is your elimination rate constant. So as your elimination rate constant increases from 0.25 to 1, you can see that the time to peak effect, or the time it reaches steady state, decreases. So the time to steady state or time to peak effect here is 14. So it's approximately about here where it reaches steady state or its time to peak effect. Whereas as you increase your elimination rate constant, you can see that the time to peak effect is 3.5. Okay, so it gets quicker. Now, the other thing that you notice is why it's getting quicker. It's getting quicker because look at where it needs to reach. So if you have a higher elimination rate constant, where it reaches in terms of plasma concentration, well, let's say it's approximately 1.25 here, is a lot lower than if it had a lower elimination rate constant, where it needs to reach 3.75 before it reaches steady state. And I hope that gives you a clue. These are the two rules I want you to have to help you understand elimination rate constant and time to peak effect. The first rule here is that time to peak plasma concentration is not the same as a higher concentration. In other words, a larger K10 or elimination rate constant means that the plasma concentration reaches its steady state or peak plasma concentration quicker, but at a lower plasma concentration, compared to a smaller elimination rate constant, which reaches its steady state or peak plasma concentration slower, but at a higher plasma concentration. So just going back again to this slide, is that a larger K10, so this is the larger one, which is 1, it reaches steady state quicker at 3.5 time, but it reaches it at a lower plasma concentration versus having a smaller elimination rate constant, which reaches its steady state, takes a lot longer to reach its steady state, but it reaches it at a higher plasma concentration. And I hope that's a light bulb moment for you guys. Now, with this light bulb moment, unfortunately, it needs to be broken, because rule number 2 is that you need to ignore rule 1 when it comes to the effect side. The reason for this is that the effect site has no influence on pharmacokinetics, because it's considered to be of small volume, that it doesn't have any effect on the actual concentration at the effect site or the plasma concentration. So therefore, having a larger elimination rate constant at the effect site does not reduce the effect site concentration like it would in plasma concentration. So all that matters is the time for the effect site concentration to equilibrate with plasma concentration. So now all we're looking at is just the time, okay? So we're not worrying about the plasma, or we're not worrying about sort of where the plasma concentration is. We know the concept. We know that a larger elimination rate constant means that it reaches equilibration faster. And that's all that matters when we talk about the effect side. So this is why for a bolus dosing, a larger KEO or a larger elimination rate constant means that the time to peak effect is correlated with a higher effect site concentration because it equilibrates with plasma concentration faster. And a smaller KEO means that the time to peak effect is correlated with a lower effect site concentration because it equilibrates with the plasma concentration slower. So this is for a bolus dose. So for a bolus dose, if you look at this diagram here, it starts decaying in an exponential decay function. And we have a large KO. So that's this one here, the green, which has a elimination rate constant of 2. And remember what I talked about, all that matters here is now the time. So we know that a larger KO equilibrates quicker. And because it's equilibrating quicker, what happens is that it's equilibrating at this point here versus a smaller KO, which takes longer to equilibrate and equilibrates at this point here where it starts dropping down. And so because the larger KO is equilibrating at a faster rate, it correlates with a higher plasma concentration, and therefore the effect site concentration is higher, versus something which has a lower KO, which takes longer to equilibrate, and therefore it's associated with a lower plasma concentration. Now, for an infusion dose, a larger KO means that the effect site concentration equilibrates with the plasma quickly, and a smaller KO means that the effect site equilibrates with the plasma concentration slowly. So again, with this example here, you've got the larger KO, which is reaching equilibration with the plasma a lot quicker than something with a smaller KO, which this one here, which is taking a lot longer to equilibrate with the plasma concentration. And this is the article, if you want to have a look at, with the different bolus in pharmacokinetics versus infusion pharmacokinetics and KO. You can also read it from Miller's as well. Now, finally, the golden rule. So I've just explained the why, but it is difficult and you may not fully yet understand the why yet, but I'm confident that if you follow these slides again, you will know this. But at least for today, if you understand the how, my goal is complete. So the how is increasing the elimination of a drug, KO, decreases the half-life as described by the relationship T half KO equals the natural log of 2 divided by KO. And that leads to a faster equilibration time. And finally, is it the elimination rate constant or equilibration rate constant? This is why it's called both. So K10 is the elimination rate constant from the central compartment. And Traditionally, it's just been known as the elimination rate constant. KEO is the elimination rate constant from the effect site, or the equilibration rate constant between the plasma and effect site. And because K10 is already defined as the elimination rate constant, to create some differentiation between that concept, that is why a lot of texts will describe KEO as the equilibration rate constant. So you'll see those two different terminologies used, and they are both correct. When we talk about K1E here, that is similar to KO, all right? And KEO here is similar to K10. And the question that I was asking Brian was that when we talk about plasma concentration, or the time to peak effect or steady state, so time to peak effect or steady state, is it your infusion rate that determines it, or is it your elimination rate constant? And the answer to this is that it is your elimination rate constant which determines the time to peak effect or steady state. It has nothing to do with your infusion rate. So you can double your infusion rate, you can triple your infusion rate, you can quadruple your infusion rate. Your time to peak effect or steady state will be the same. But if you change your elimination rate constant, you are going to be changing the time to peak effect or time to steady state. And that's where it's analogous to KEO. So that's the relationship with that. And it just goes on to follow from with this slide here. And you'll see it with many sort of basic pharmacology textbooks where they talk about the time to steady state is dependent on a drug's elimination half-life. And a drug's elimination half-life is related to your elimination rate constant through that formula, T half equals 0.693 divided by your elimination rate constant. And so it is the half-life, the elimination half-life of a drug, which determines the time to steady state or peak concentration. It has nothing to do with the infusion rate. I think that's a really, really good question.